Hello, welcome back again in my course, Intelligent System, Week 3, Local Search. In this week, we're going to talk about the hill climbing, simulated annealing, and genetic algorithm. Last week, we already discussed about the partial searching, where we seek a goal node and construct a path from the start to a goal state. So we only consider some part of the node to construct the best path, the best solutions. It includes BFS, DFS, UCS, greedy best search, and A-star. Okay, in a complete searching, it's a little bit different. Now we consider a node here is a solutions. So the whole graph is a set of solutions, the possible solutions. The operators can go from one solution to another solutions and find the best solution from the alternative. This is the local search where they can only consider the neighborhood, searching in the neighborhood. They can only see what happened within this neighborhood. Different with global search where they want to find another solutions, the whole set of possible solutions. The neighborhood should be much smaller than the size of the search space, otherwise the search degenerates. So yeah, why we need to localize the search? Because we want to find the better solution quickly. Okay, so in order to find the best solution, the better solutions in the neighborhood, we need to apply some tests according to the score. How the score being calculated is by using a function called f of n that is used to map each solutions to a number. For example, in a problem where travel salesman problem, where somebody needs to travel from one place to another place, and we need to calculate the best distance, the shortest distance from the start place to the destinations. That will be finding the minimum score of the function f of n. So there are two ways to find the best solution. It can be either maximizing the functions or minimizing the function. The one that maximizing the function called hill climbing or gradient ascent in continuous data. And the one with minimizing the functions f of n called valley finding or gradient descent if continuous. So for TSP, we consider the problem as minimizing the f of n. For example, like this. Each node represents the solutions. Each node represents the solutions. And then in the valley finding, the current node is ABC, for example. They start from this node. The operators is to swap consecutive cities. So just swap between the next cities. So in this case, they swap the first two, BAC. Okay, so the distance is symmetric. They calculate A to B equals to 2, and then B to C equals to 3. So ABC means 5. BAC equals to 2 plus CA1 equals to 3. So the distance will be 3. So the aim of the valley finding is looking at the neighborhood, whether 4 and 3, which one is lower, and then they see, okay, 3 is lower than 4, then I go to the next node, which is this one. Once they reach this node, and then they assess again the neighborhood. Okay, I see this is greater than 3, this one also greater than 3, then my algorithm stops. And I found this is the best solutions. Okay, so as the opposite of valley finding, there is an algorithm called hill climbing, you climbing. you climbing up to you find the peak point here. So you need to guess what is the x, element of x, and then and your neighborhood. Please repeat let n equals to the argument maximizing the n element of n, f of n. If f of n greater than f of x, which map x equals to n, else you stop. So basically you want to maximizing this f, yeah, f of x. So if your current state is here, then you look at your neighbor, whether you move to the left or to the right. Okay, because my right neighbor has the highest value of f of n, then I choose the right neighbor. And then I keep climbing up to the peak point, the peakest point. Okay, there is a problem with this kind of algorithm. Hill climbing can get stuck in local maxima. What is local maxima? Local maxima meaning that you can stuck in something like this. Yeah. If you get on this point and then you see the neighbor, okay, in the left side, your neighbor is less than the current state, and then your right side also less than the current state, then you cannot move anymore and the hill climbing algorithm would stop. Okay, we don't want something like this. They can also get stuck in plateau like this in the flat local maximum or in a ridge like this. So we don't want something like this. We want to escape the local maxima. There are two ways to escaping the local maxima by either choosing the neighbor randomly or accept the neighbor if it is better, or if it is not better, accept with some fixed probability. So you can always accept the neighbor even though it's worse, but with a lower probability, because it can lead you to another neighbor which is higher than the current state. Like this, for example. Now we only we consider not only the local neighbor. For example, this is your current state, and then you consider also the neighbor in here, in here. So it's random. Okay, so now, for example, this is my first, my initial point, initial state, and then I move to this one. After I move to this one, I check, okay, so this is better, I accept this one. For example, after this one, my current state is here, and then after this point, I pick randomly again my neighbor, and I get stuck in here, which is worse than the current state. I will think about the how to accept or not to accept. So that's why I assign the probability. I assign the lower probability to accept this as the next node. Okay, so for example, I accept this as the next node. And then I assess again the other neighbor, and then I assess again the other neighbor, and then I assess again the other neighbor, and then finally I can reach to the top. And how can my algorithm works and stop at the very peakest point? There is an algorithm called simulated annealing. It picks a neighbor at random and either rejects or accepts the new assignment. Annealing is a process in metallurgy where metals are very slowly cooled to make them reach a state of low energy where they are very strong. So if you see the metals, yeah, and then the metal is very hot in the liquid shape, yeah, form, and then when it's cooling down, it become hard, and it finally reach the solid state. When it's reached the solid state, the temperature become very low. That's the point of the annealing. That's why some researcher invent the simulated annealing, which is a process where the temperature is reduced slowly, very slowly, starting from a random search at the high temperature, eventually become pure greedy descents as it approaches zero temperature. At the high temperature, worsening steps are more likely than at lower temperature. So they're using this probability value to accept or to reject a node, the neighbor node. They're using the exponential value. So whenever the temperature, whenever the temperatures goes to next to very low, very low, very low, very low, then the probability will be reaching zero, also very low. So this is what the simulated annealing do, right? Probability equals to exponential value of x, the same like this one. So with the base of e number to the power of h of a minus h of a prime. A is the current node, a prime is the neighbor, and h is the functions. And then you divide by the T temperatures, and you can calculate something like this. If your temperature is 10, and then the difference of your neighbor and the current state is only one time worse, that means this is -1 because it worse, this is minus. If you fit this number -1 and replace, substitute this formula with the number -1, and then over T, the temperature 10, so minus 0. I'll draw this. Okay, so it's become e to the power of, because this is -1, divide by 10 equals to e to the power of minus 0.1. This number equals to this one, 0.9. Okay, it's a little bit different with this one. E, for example, how many times worse? Okay, I say 2 times worse. So 2 times worse, meaning that e minus 2 divided by 10 equals to e minus 0.2 equals to 0.82. So if we see another, this one, how many times worse? So for example, only 1 time worse, for example, in here. But if it's 3 times worse, 2 times worse is here, or even like this, 3 times worse in here. So if we see the probability of accepting this node as your next state, and the probability of this one is higher, 0.9, and this one is only 0.87. So I will accept this neighbor more than this neighbor. So I will pick this neighbor as my next state. So this is what the number said, yeah. And then what happened if the temperatures goes down to 0.1? So in the simulated annealing, every iterations, you assign the different temperatures, starting from the initial temperature, any kind of initial temperature. For example, you start from 100 or 10, and then you end up with T equals to 0. So every time you run the one cycle of simulated annealing, you assign different value of temperatures. Okay. Now, how about if the temperatures closer to 0? The probability of accepting the solution that is worse than the current state, the current solutions, the current state is even lower, very, very, very low, like this. Maybe in this area. And it's become 0, 0, 0.0 something. This is very, 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 very low. So in the last iterations, the simulated annealing can get only in this one, only in this position. They're no longer accepting the worst like this, the worst point, because the temperature is closer to 0. So whenever they found something next to the peak point, they can always find the peak point, and then they finally stop. Why stop? Because they don't want to accept any more solution that is that is worse than the current solutions. That's why the simulated annealing can find the global maxima like this. Temperatures goes down, 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 down. And then look at this. This is keep stuck in here. Finally 0, and this is the best score that they can found. Okay, start again. Very quick, very quick, very quick, very fast, very fast, very fast. Getting slower, 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 slower. And stop. Okay. That's about the simulated annealing. Okay, so the third algorithm is called genetic algorithm. So this is another approach to find the global optima by looking at the neighbor. Okay, so actually this algorithm inspired by the nature, yeah. Based on the algorithm that based on the concept of natural selection and genetics. So in the world, yeah, there is a theory of evolution by Darwin and Lamarck. Evolution of species, survival of the fittest, that say that the one that can survive is only the one that has the best gene. Yeah. In genetic algorithm, the data will be represented like this. This is the gene. A single bit is a gene. And then a set of the gene called chromosome. And then a set of chromosome called the populations. The whole of this is called populations. And this is my neighbor. This is my neighbor. This is also my neighbor. I want to search the best solutions by exploiting my neighbor. So it follows this cycle. From the populations, from the initial populations, and then we evaluate the parents by assigning the fitness value, and then it goes to the reproduction, and then crossover operation and mutations, and then the offspring that produced by these operations will be sent back to the populations to increase the whole population's fitness value. So in order to do this, we need to do the first step, which is the selections. With the selections, the idea is to select the fittest individual and let them pass their genes to the next generations. So we pick 2 individuals as the parents based on their fitness score. Yeah, instead of just sorting the parents based on the fitness value, we still use, remember, we still use the random, yeah, random principle. So we assign the fixed point in here. We assign a fixed point, and then we assign the big part of this for the chromosome with the highest fitness value. And then, for example, this and this will be the B, and then this one will be the E, yeah. And then this one will be A, B, and this one C and D. This is D, this is C, and then this one will be F. the smallest. So I spin the wheel, and then the wheel is moving, and then finally at the fixed point, the wheel stop in here at the D. Why I only give them like this portion? Because this is only 1.4, 1.2. So because my wheel stop in here, I choose D as the parent, D. Okay, so with that kind of process, yeah, selection process, I can have two parents. For example, I have A1 and A2, and then I can apply the crossover operations. Crossovers meaning that I pick a point here. For example, this is my crossover point, and then I generate my new offspring. The offspring is, yeah, I swap this and then send the value down. And this one, I keep this the same. So it become 1, 1. Oh, sorry, it become, yeah, 0, 0, 0. And this one become 1, 1, 1 from this one. Initially, they are 1, 1, 1. It become on the top, 1, 1, 1. So now I have new generations, which is called A5 and A6, no longer A1 and A2, but A5 and A6. They are kind of different solutions. Okay, we can also apply the mutations operations. The mutations meaning that we just convert the bits from 1 to 0, 0 to 1, 0 to 1, like this. And it's happened randomly. The terminations, the algorithm terminates if the population has converged. It does not produce any offspring which are significantly different from the previous generation. Remember, the goal of the genetic algorithm is always to improve the populations. Yeah. I want to always improve the populations. If the population doesn't change anymore, selection, crossover. If the population doesn't change anymore, doesn't improve, then this algorithm stop. Then it is said that the genetic algorithm has provided a set of solution to our problem. So this is after some iterations and the algorithm stop. This is the best population that we can have from the genetic algorithm. Then finally, you can pick and sort them by the fitness value. For example, okay, so now if we talk about the 8 queens game, 8 queens game, the rules of the game is you need to arrange the queen so that there is no other queen that can attack each other. So for example, attack is, okay, this one attacking this one. So this is still not done. Yeah, this is can attack the other queen. So you need to place this one. You need to move this queen to another positions as long as they don't attack each other. Okay, how we apply the genetic algorithm in this case? So first, we need the representations, yeah, as the chromosome representations. I use the calculations of the distance. For example, the distance from the base for this queen is 2 because 1, 2, I put 2. 1, 2, 3, 4, I put 4. And then the next digit is 1, 2, 3, 4, 5, 6, 7. I put 7. The next digit 1, 2, 3, 4. I put 4. Okay, so that's my string representations. With these string representations, we need to know how to calculate the fitness score. So how good is this bits. How good is the bits? According to the position that is not attacking each other. Okay, I will calculate based on the number of the other queen that is not attacking these bits. For example, this one. Okay, I cross this out. And how about the diagonal one? No. How about the vertical one? No. And then the rest is the fitness score 1, 2, 3, 4, 5, 6, because this other 6 is not attacking my queen. So I put this one 6. How about the next bits? This one. Okay, let's check. I'm not on. I no longer considering this one. Yeah, otherwise it will be redundant. Okay, so with this second bits, I can see that this is attacking my queen. And then that's it. So the rest is safe. 1, 2, 3, 4, 5. I put 5. The third bits here. Okay, it's safe. Yeah, nothing can attacking my queen. So I remove this from my calculation because I already calculate this. So from this position, I have 1. Okay, so this one is attacking my queen, so I disregard this one. So I count the rest 1, 2, 3, 4. So I have 4 in here. Okay. Next. So I have the chromosome already. In here, I have the chromosome already. I have the fitness function already. How to calculate that is, yeah, as earlier, I mentioned earlier in here, you have this number and you have the string representations. And you also have the probability. We found the probability from the roulette wheel, yeah, the selection process. Based on the selection process, I can see that this individual, this chromosome, the probability is higher because this has the best fitness function. So I pick this one, this guy as the parents. And then I also pick this one as the parents. I don't want this guy because this guy only have 11 as the fitness function. And I also pick this one. Once you know the parents, you can start to do the crossover and mutations. The crossover meaning that you pick a point and then swap these bits and these bits. So yeah, the white part and the gray part. The same with this one. And then after that, you apply mutations. You just change bits in here randomly. Now you have a new generations of spring. You send this back to your populations. And then you start again this process and keep it in cycle until your population doesn't improve anymore. Okay, that's it for today for these sessions. You can try the exercise by try to find the word bad from the population of the first 5 alphabet A, B, C, D, E. And you can define the fitness score as the number of characters which differ from characters in target strings in a particular index. So for example, EDC, because E, D, and C, you have 3 misplaced misplaced letter, so you give them score 3. If BAC, you only have 1 incorrect letter, so you give them score 1. The algorithm will stop if it found the offspring with the fitness equals to 0. So you can try this. Okay, that's it for today. Thank you very much.